Before we do example 13, we're going to need to know a fact about circles. If you've got a circle and an exterior point, and you label on the point that's on the circle and is closest to this point A, so this point here, we know that this point is going to lie on the line that goes from A to the centre of the circle. And that will be true no matter where we draw this circle. A similar thing is true for the point that's furthest away from A on a circle. So if we've got a point here on the circle that's furthest away from this exterior point, then this pink point that I've just drawn is going to lie on the line that goes from the exterior point through the middle of the circle. Okay, and again, that will be true no matter where the circle is drawn. I'm not going to prove these two facts right now because it's not necessary to know why that is for the time being. We'll just use these facts, but I'll prove it at the end of the video. So we've got a complex number z which satisfies this equation here. So you could do it algebraically or geometrically. Let's do it geometrically. So to work out what this locus of points will look like geometrically, to work out where z needs to be, we're always going to write it as z minus and then some complex number. So inside the modulus we're going to have z minus, and then inside the bracket we need 12 plus 5i, because when we expand this bracket we're going to get minus 12 minus 5i. So remember the interpretation of this: if you have the modulus of one vector, 1 point complex number, take away another complex number, that's the distance between the two complex numbers. So the distance between z and 12 plus 5i is equal to 3. So we need to draw an Argand diagram and sketch on all the points z that are a distance of 3 away from 12 plus 5i. So let's put on 12 plus 5i. And all the points z that are a distance of 3 away, they're going to lie on a circle of radius 3 around that centre point. Let's just check that that makes sense. Let's say we've got a point on the circle z. And remember that this can be thought about as a vector. This is the vector that goes from 12 plus 5i and takes us to the point z. So that's basically that vector there. And we're saying that that length is equal to 3, which it is because the radius of the circle is 3. So this is our point 12, 5. So that's the locus drawn. What the question is saying is we want to find what's the minimum possible value for the modulus of z. So we can think about z moving around this circle. And as z moves around the circle, the modulus of z is going to change. Remember, the modulus of z will be the distance from z to the origin. So if z was there, for example, the length of this green line would be the modulus of z. So I've got an animation here to help us think about this. The length of this dotted line is the modulus of z. How far away from the origin is it? So you can see as we move around this circle, as z changes, the modulus changes. Now we want the point at which the modulus is as small as possible. That's equivalent to saying we want the point on the circle that's as close to the origin as possible. So that's that point there. And we know, because of the fact that we learned at the start, that this point here is going to lie on the line that goes from the origin to the centre of the circle. So we've got the diagram here, and that basically means we want to find out what is this length here. Let's call this length d. So d is going to be the min value of the modulus of z. Okay, so we know that this point lies on the straight line, so we could extend this straight line, and we know that that's going to go through the centre of the circle, because that's the theorem that we saw at the start. Okay, so we know that this portion of the line from Z to the centre of the circle is just the radius of the circle, which is a length of 3. So you might be able to see that we can do a bit of problem solving here. We know that we can draw in this right angled triangle, and we can work out what the hypotenuse of this right angled triangle is. So we know that D plus 3 is equal to the hypotenuse of this right angled triangle, but we know that the vertical length on this right angled triangle is 5 and the horizontal length is 12. So we know that that is going to be equal to the hypotenuse of the right angled triangle, which is the square root of 5 squared plus 12 squared. So we know that D plus 3 is equal to 13. So we basically said that on this right angled triangle, this length here is equal to 13. So we know that D must be equal to 10. So the modulus of Z min is equal to 10. We can do a similar thought process with finding the maximum value of the modulus of Z. So we want the point on the circle where Z is as far away from the origin as possible, because that'll be the maximum value for the length of this dotted line. And that's going to happen, we know that's going to happen when the line to the origin passes through the centre of the circle, because of the theorem that we looked at the start. So we're basically working out what's the length of this entire dotted line. Well, we know this portion of the circle is 3, and we already had worked out this part was 13 because we drew in this right angled triangle and we knew this length was 12 and that length was 5, so the hypotenuse was 13. So straight away you can see that Z is 13 plus 3 away from the origin. So the maximum value, the modulus of Z, is 16.